We continue with chapter 23, which is all about amines, and we want to look at the preparation of amines. How do we make amines from other compounds? So we can make amines using nucleophilic substitution on an alkyl halide, and the nucleophilic substitution is SN2. Right? And here are some examples of the nucleophilic substitution that we can do. So if we take an alkyl halide and we treat it with ammonia, we can get the alkyl ammonium ion, which we can then deprotonate to give us a primary amine. So if we start with ammonia, we can get a primary amine. So every time we do this, we make a new carbon-nitrogen bond, and some limitations on this. Because this is an SN2 reaction, we're going to need a pretty much sterically unhindered carbon on this. So we're going to be limited to like methyl halides and primary alkyl halides. If you're going to try it with a secondary halide, you probably are going to have some trouble. So SN2, keep that in mind when we're doing it. If we have a primary amine and we treat an alkyl halide with that, we can get the secondary ammonium ion, so secondary alkyl ammonium ion, and then we can deprotonate that and get the secondary amine. We can go another step with this. So take a secondary amine and treat an alkyl halide. We can get a tertiary amine by doing the subsequent steps. And then finally, and this happens, we can have a tertiary amine that reacts with an alkyl halide, and we can form a quaternary ammonium salt. One of the issues with this is that when we attempt to do this, where we have ammonia and we attempt to do this nucleophilic substitution on an alkyl halide, we tend to do more than one of these alkylation steps. So it's hard to just stop at one. Now, it's possible, but it's a little more challenging. Because of all this polyalkylation, this is a very useful method for making quaternary ammonium salts, and not quite as useful for like making a primary amine or a secondary amine. That said, it is one of our possibilities. We're going to look at something that is related, and what it does is we're going to use what's called the Gabriel synthesis. And the Gabriel synthesis, instead of using an amine as our nucleophile, we're going to use something that we refer to as phthalimide, and we're actually going to use the conjugate base of phthalimide. So here is phthalimide. It has a acidic hydrogen that is on the nitrogen. The reason it's acidic is that we have these two carbonyl groups. When we deprotonate and we get the conjugate base, that conjugate base is resonance stabilized. So we can put the negative charge not only on the nitrogen, but on each of the oxygens. Because we've got those three resonance structures, that means this is pretty acidic. pKa of 10, I mean, it's not the most acidic thing in the world, but it is decently acidic. It's also a pretty good nucleophile. So if we take this and treat a primary alkyl halide with it, we can do alkylation of that nitrogen. And when we do alkylation of that nitrogen, we will get an alkylated imide. So we'll get that alkylated imide. That alkylated imide, we can then do a hydrolysis, a base hydrolysis with it, and we will get the primary amine. This is an effective method for making primary amines. Typically, you're going to do this where you're going to do this with alkyl groups that are more complicated than something like ethyl or methyl or propyl. You're probably going to do it with something that maybe you have spent a little bit of time with, and then you go through this process so that you can get that primary amine. It's really only effective for making primary amines, so we're not going to be able to make secondary amines using this particular method. But don't worry, we have some other tricks that we can do. So let's look at number 7. Number 7 is really, really easy. In fact, it's probably too easy. It's probably too easy. And you may be thinking, no, that's not possible. How could this be too easy? Well, since, I mean, here we're not even showing what the phthalimide looks like. We're just looking at what alkyl group do we need to make this primary or to make each of these primary amines. So we want to say what alkyl halide. Well, to do this, the alkyl halide is going to be this with a halide there, and we can choose whichever one we want. I'm going to choose bromine. So 1, 2, 3, 4, 5, 6, 7. All right, so we've got those 7, and then here we'll just put bromine, and that's how we do this. So choosing the alkyl halide to use in your Gabriel synthesis is a really easy trick. All right, again, here we're just going to replace that with an alkyl group. Again, I'm going to choose bromine. Easy to do. Same thing on this one. We're just going to change that out for a bromine. So OCH3, and we have 2 carbons there, and then we'll put a bromine. All right, and that is how we do the Gabriel synthesis. So pretty easy reaction to do. All right, let's look at the reduction of other nitrogen-containing compounds. And so we can take a nitro group. We saw how to do this previously. I don't remember what chapter it was, but we can take a nitro group and do catalytic hydrogenation with it to give us a primary amine, or we can choose a metal with HCl like iron or tin. You can also inadvertently do this with your Clemmensen reduction conditions, but that's not as effective as these. So I would probably go with the catalytic hydrogenation or the iron with HCl, the tin with HCl as a choice here. So you can make primary amines using nitro groups doing this. You can also use a nitrile to make a primary amine. And we talked about this one earlier when we looked at the chapter on nitriles. We can use lithium aluminum hydride followed by water, and that will stop and give us a primary amine. Very useful way to make primary amines. Since nitriles are fairly easy, relatively easy to make, I will say. All right, we can also take amides and reduce those into amines. And this is really easy. If you take a primary amide, you'll get a primary amine. Secondary amide, secondary amine. Tertiary amide, tertiary amine. All of these, lithium aluminum hydride followed by water, and you will get the corresponding amine. So let's look at number 9. So what nitro group, or what nitro compound, nitrile, and amide are used to make each of these. Let's start with the nitro group. We're just going to replace that NH2 with a nitro group, and there we go. For this one, again, it'll just be a nitro there, NO2. And this one, 1, 2, 3, 4, 5, 6. So we have 6 carbons, so we'll make 1 nitro hexane, so 3, 4, 5, 6, NO2. All right, as far as the nitrile, we're going to, the carbon in the nitrile is going to be this carbon. So that nitrile will give us this when we do reduction with lithium aluminum hydride. All right, and for this one, again, it will be this carbon, so we'll just do a cyanocyclohexane. And on this one, there'll be 5 carbons plus the nitrile. So 1, 2, 3, 4, 5, and then CN. So it is important to remember that this carbon is going to be that carbon right there. So we have to adjust the number of the other stuff that's attached to it. All right, and then just as a reminder, this first one we could use hydrogenation, so palladium on carbon, and then for these we can use the lithium aluminum hydride, step 1, step 2, followed by water. All right, so let's look at the amine. So again, we're just going to make that the carbonyl. So whatever the adjacent carbon is, that's the carbonyl. NH2 will give us that. For this one, this would be our carbonyl. And then finally, for this one, that would be our carbonyl. and that would give us an amine when treated with lithium aluminum hydride followed by water. All right, so now let's look at reductive amination. Look at that word carefully. There's a pretty good chance that up until this point in your life, you have not seen the word amination unless you have taken an organic chemistry course before. Amination, it looks a lot like the word animation. The M and the N are reversed, but it is amination. So reductive amination, it's a two-step process where we take aldehydes and ketones, and we can convert them into either primary, secondary, or tertiary amines. It all depends on what we start with as far as the amine goes. We're going to look at this particular one where we take an aldehyde or ketone. So here is an aldehyde or ketone, just depending on what they are. This alkyl, whether it's an alkyl or hydrogen here. We treat it with ammonia and a reducing agent. There's an imine that is formed. We do not isolate that imine. And we have a reducing agent that we put in at the same time, and that reducing agent will convert this imine into an amine. So imine to an amine. All right, so there we go. We get a primary amine. So if we start off with ammonia, we can get a primary amine. Let's look at that special reducing agent. That special reducing agent is called sodium cyanoborohydride. So sodium cyanoborohydride. It is a reducing agent that works very well for this particular application. So, so here, again, we have some with ammonia. This is acetone. So we've got 3 carbons there. We're essentially going to replace this carbonyl with a nitrogen, and we'll add a hydrogen to that carbon as well. So we're getting rid of the carbonyl and replacing it with a hydrogen and whatever our nitrogen group happens to be. You'll notice that we don't have steps here. We just put them all in at the same time, which is actually kind of cool. Here, if we've got this particular compound, this is phenylacetone. Phenylacetone, if you treat it with this ammonia and this sodium cyanoborohydrin, you can get this illicit drug. I'm going to talk about this here in just a second. And the reason I'm going to talk about it is because I don't want you to get any ideas of thinking, ooh, I could make illicit drugs. No, don't do it. All right. Reductive amination to form primary or tertiary amines. It's really just a matter of what your starting material is. If you use a primary amine as your starting material, you can get a secondary amine as your product. If you use a secondary amine as your starting material, you can get a tertiary amine as your product. So here we've got this ketone or aldehyde. It could be either. Treat it with a primary amine. We will get this imine as an unisolated intermediate. The sodium cyanoborohydrin will reduce that imine to a secondary amine. And likewise, we can take a ketone or an aldehyde, treat a secondary amine, we'll get an iminium ion, which can then, again, and that was not isolated, and the sodium cyanoborohydride is going to reduce that to a tertiary amine. All right. So always note the result. We're going to replace one hydrogen and a nitrogen on a nitrogen atom and attach it to an alkyl group. So we're essentially breaking the nitrogen-hydrogen bond. We're going to make a new bond between nitrogen and the carbon, and we'll make a new bond between carbon and a hydrogen. I would say it's this hydrogen, but it's not that hydrogen. It's actually one of these hydrogens, but that's details. Here is an example of using reductive amination using the cyanoborohydride, the sodium cyanoborohydride. So you can take amphetamine or methamphetamine. You can make those using the reductive amination. So this is the phenylacetone that I talked about a little bit earlier, and you can treat that with this primary amine and sodium cyanoborohydride, and you can get the secondary amine, which is methamphetamine. All right, this is where I make a little statement here about This starting material, the phenylacetone, is tightly regulated. It is a Schedule II controlled substance. It in itself is not a drug, but it is a Schedule II substance. If you attempt to order this, they're going to know. They do monitor who purchases it, and you are subject to inspection if they deem that necessary. They can do that with a warrant. So don't get any ideas. This is a bad idea. It's dangerous to do if you don't know what you're doing. It can be hazardous, and also you don't want to make illegal drugs. All right, that's my little talk about don't make drugs and don't do drugs. We're going to look at doing retrosynthesis with these. So we'll talk about retrosynthesis of these compounds using reductive amination. So with the retrosynthesis, really, it's pretty easy. You just need to keep in mind two things. One alkyl group and on the nitrogen comes from the carbonyl compound, and any other alkyl groups are going to come from are going to be on the nitrogen to begin with. So for example, if you want to make a tertiary amine where these are both alkyl groups, then you need to start with a secondary amine. This particular carbon-nitrogen bond is formed. So if you cut that, this carbon is going to become your carbonyl carbon on your carbonyl compound, and the rest of it is going to become your starting amine. So remember, every time you do this reductive amination step, you're going to increase the number of alkyl groups on your nitrogen by 1. Now, one quick note about this. To do this synthesis, your product needs to have a hydrogen on the carbon that is bonded to the nitrogen. If this happens to be a tertiary alkyl group, so you have 3 carbons attached, it won't work by this synthesis, and you'll have to make that part of your starting amine instead of forming it by reductive amination. All right, so here let's look at another example. If we want to make 2-phenylethanamine, so 2-phenylethanamine, there's only one particular bond that we could form by the reductive amination. So it's this bond, which means our starting amine is going to be ammonia, and our starting carbonyl compound is going to be where we have carbonyl here, which is going to be this aldehyde. So phenylacetaldehyde would be our starting material there. All right. If you're doing retrosynthesis with a secondary or tertiary amine, that means that you may have some choices. So there may be more than one possible synthetic pathway. Let's look at this particular secondary amine. So here we have a cyclohexyl group, and here we have a phenyl group. The name of it is N-ethyl cyclohexanamine. So the choices we have are that we could form this carbon-nitrogen bond between the cyclohexyl group and the nitrogen. If that's the case, then the cyclohexyl would have been our carbonyl compound, in other words, cyclohexanone, and this other component here would have been our amine, so we would have started off with ethylamine and cyclohexanone. Our other choice is this. If we've got if we form this particular bond, then our amine would have been cyclohexanamine, and our starting carbonyl compound would have been acetaldehyde. Now, sometimes we're going to find that one of these pathways may be easier to do. You may look up and see what ingredients you have in your lab, and you may have one of these carbonyls but not the other. You may have one of these amines and not the other. So that's something to keep in mind when you are preparing a synthesis, is what is available either in your lab or that you could potentially order. All right, let's look at number 49 on the assignment. All right, so here we want to draw the product of each of these reductive amination reactions. Again, this is pretty easy. all you have to do is find your carbonyl compound, and we're going to break that carbon-oxygen double bond. So we're going to break the carbonyl, and we're going to make a new bond between nitrogen and that carbon. And that's pretty much it. That is pretty much it. So here I'm going to go ahead and draw our phenyl ring there. So we've got that. And so here, this is where we make the new bond. So we have 3 carbons attached to our phenyl group, and we've got a nitrogen. And then it's just a matter of putting the other stuff in. So there will be 1 hydrogen remaining on your nitrogen, and then 1, 2, 3, 4 carbons from our starting amine. And so that would be our product. All right, here we've got a cycloheptane or cyclohexanone as our starting carbonyl. Again, we're going to break that carbonyl, and we'll have a new bond between nitrogen and that carbon. Since this is a secondary amine, that means our product is going to be a tertiary amine. There's something about drawing 7-membered rings that mine always come out ugly. So just trust me, there are 7 rings on there. You can probably do it better if you have a template or I don't know, just practice. So we'll have nitrogen attached there, and we'll have 2 methyl groups. I'll put 2 methyl groups on there, and that would be our product of that reaction. All right, here we have phenyl, CH2, 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 and then this aldehyde. So we've got 4 carbons attached to that phenyl group. I'll go ahead and draw the phenyl. So 1, 2, 3, 4. All right, and then attached to this, we're going to have a nitrogen. And since this is NH3, our product is going to be a primary amine. And so that would be the product of this reductive amination. It's always worthwhile just to double check, make sure. So I've got the 6 carbons here in the ring, and then 1, 2, 3, 4 carbons there, 1, 2, 3, 4 carbons there. Always make sure you have the correct number of carbons when you're doing one of these syntheses. All right, so here is our ketone. Again, we're going to break that carbon-oxygen double bond, and we're going to have a new bond between nitrogen and that carbon. So this is kind of an unusual looking compound, but 1, 2, 3, 4. There is our nitrogen. We have hydrogen there. And then we have a cyclohexyl group that's attached. All right. Since we started off with a primary amine, we're going to have a secondary amine as our product. All right, and that is how we do reductive amination. Reductive amination. So let's look at a couple of the reactions that amines will undergo. And there's 2 important kinds of reactions that amines undergo. The first is that amines will undergo acid-base reactions. Amines, first and foremost, they're bases. They have a lone pair of electrons that can act as bases. But they also are nucleophiles. So it turns out that among our period 2 elements, the nitrogen is typically the most basic and the most nucleophilic. So we're going to find that nitrogen is more basic than the oxygens, provided that they have the same charge. And again, that nitrogen will be more nucleophilic than the oxygens. And same thing with fluorine. So if the amine acts as an acid, it will act as a Bronsted-Lowry acid, where it will, if the amine acts as a base, not as an acid, if it acts as a base, it will deprotonate our Bronsted-Lowry acid, so it will be an H+ acceptor, and our acid here will be an H+ donor. We'll talk about what kinds of acids can do this here in a few minutes, but turns out quite a few. We'll get an ammonium salt as the product of that. And if it acts as a nucleophile, so if the amine acts as a nucleophile, it can react with an electrophile, some sort of electrophilic carbon, like an alkyl halide. We've already talked about that a little bit. It can react with alkyl halide, and if it does that, then we potentially could make a quaternary salt, a quaternary ammonium salt. Now, if this is not tertiary here, then it could still act as a nucleophile, and we could get something less than quaternary. But this is one of the ways. This is essentially the way that they make quaternary ammonium salts. All right, so let's look at amines as bases first, determining what direction will the equilibrium lie when we have an amine as a base. We don't have to have a super strong acid for an amine to react with it. So here we have a typical amine. This is just an alkyl amine of some sort. We don't know what the alkyl group is. And we have an acid, a Bronsted-Lowry acid. When that Bronsted-Lowry acid protonates our amine, the conjugate acid that we get is called an ammonium ion. It's the conjugate acid of this base. And for most of our typical amines, that conjugate acid is going to have a pKa in the range from 10 to 11. Well, just as a reminder, the larger that pKa value is, the weaker the weaker this is as an acid. So the weaker this is as an acid, the stronger this is as a base. So with a pKa of about 10 to 11, that's not a very strong acid. If we look at this acid, if this acid has a pKa less than 10, we're probably going to protonate most of this and get mostly product in this acid-base equilibrium. So as long as the pKa of our acid is less than 10, we're probably going to protonate alkyl amines. Here are a couple of examples. Ethylamine, when we protonate it with HCl, so HCl, strong acid, look at that, pKa -7. So when we protonate that, we're going to get ethyl ammonium ion. So ethyl ammonium ion. The ethyl ammonium ion has a pKa close to 11, 10.8, but we'll just say close to 11. And the pKa of the other acid, the one on the other side, was -7. Well, whichever one of those is lower must be the stronger acid. So HCl is a much stronger acid than the ethyl ammonium. Well, the equilibrium is going to lie opposite the side of the stronger acid. So since this is the stronger acid, the equilibrium will lie to the right. Similarly with this one, here we have triethylamine. Triethylamine put in with acetic acid. Acetic acid has a pKa of 4.8. We protonate that triethylamine and we get triethyl ammonium ion. Again, pKa of around 11. That's very typical for our alkyl amines. So pKa of about 11. And our pKa of our original acid was 4.8. That means the acetic acid was a stronger acid than our product triethyl ammonium ion, which means the equilibrium is going to lie opposite the acetic acid. In other words, it will lie to the right. So definitely the first reaction is going to be further to the right, but these are both going to be almost all products. You're going to have 99+% products for both of these. Just for the top one, it's going to be like 99.9999% product. All right, let's look at number 16 on our in-class assignment. And on this one, we're going to look at some acid-base reactions. We're going to write out the products of some acid-base reactions, and we're going to determine what direction the equilibrium will lie. So here we've got butylamine. So 1-butylamine. We're not sure exactly what the pKa of this is, but it's going to be pretty close to 11. So our pKa of its conjugate acid. Let's go ahead and draw that conjugate acid. So 1, 2, 3, 4. NH3 plus, and then the conjugate base of HCl is going to be the chloride ion. If we look at the pKa's of this, HCl has a pKa of -7. And then the ammonium ions, or the alkyl ammonium ions, in this case butyl ammonium, is going to have a pKa of about 11. It's about 11. I don't know if it's exactly 11, but that doesn't really matter. When we look at these two numbers, -7 versus 11, -7 is definitely lower. HCl is a stronger acid. The equilibrium, will be to the right. So to the right. The equilibrium will lie far to the right. So -7 versus 11, equilibrium to the right. All right, let's look at this one. Here we've got, we have benzoic acid, and this is dimethylamine. So let's go ahead and draw the products for this. So our dimethylamine will be dimethylammonium. So we'll have 2 methyls and 2 hydrogens, positive charge there. And then the conjugate base of this is going to be benzoate. All right. And now we're going to compare pKa's. So pKa of acetic acid is usually going to be in the 4 range. It just so happens for this one, and we saw this one in an earlier chapter, has a pKa of 4.2. Now, if you had said 4.8 because you confused it with acetic acid, that's fine, right? We just need to know the ballpark for it. If you said anywhere between 4 and 5, you're good, all right? The pKa of this, again, I don't know what exactly it is, but it's about 11, all right? So when we look at those two numbers, 4 is less than 11, so this equilibrium is going to lie to the right. So definitely product favored. All right, for this last one, our acid here happens to be water. So our acid happens to be water. Our base is this piperidine. So, so piperidine reacts with the water. We're going to get the piperidinium. All right, so piperidinium. And the conjugate acid, or conjugate base of this acid, is going to be hydroxide ion. All right, when we look at the pKa's of each of these, I know that the pKa of water comes out to 15.7. And I looked this one up, and I found online on a reputable website, this one had a pKa of 11.2. Then I looked later in this textbook, and it has a pKa of 11.1. We're going to go with this textbook, but it's around 11 again. So again, you'll notice all of these were around 11. We look at these two numbers, 15 versus 11. 11 is a bigger number, or a smaller number. It is a smaller number, which means that the piperidinium ion is a stronger acid than water. So here, the equilibrium will lie to the left. So this is a stronger acid. Equilibrium will lie the opposite direction. Okay, well, let's look at extractions of amines from an organic layer. We've talked about this before. So we've talked about doing this with carboxylic acids. And so now we're going to look at doing this with amines, with a base. So here's the important information. So here we've got cyclohexanamine. Cyclohexanamine is going to be insoluble in water. It's got 6 carbons. Usually to have solubility in water, we're going to need to have this like less than 5 carbons. So with 6 carbons, that's going to be insoluble in water. And it's going to be quite soluble in dichloromethane. So we can get this to dissolve in dichloromethane, but not in water. If we treat this with an acid, and here we're going for the big guns, we're going for hydrochloric acid, which is a pretty strong acid, that's going to protonate this amine and convert it from cyclohexanamine to cyclohexanammonium chloride. And so this is now an ionic compound. We've got this alkyl ammonium chloride, and that is going to be soluble in water and insoluble in dichloromethane. So now we can use that to our advantage if we want to extract this amine out of an organic layer into an aqueous layer. We can do that by treating it with acid. Let me show you the protocol. All right, now we did a similar method to this back in the back in chapter 19, we talked about separating carboxylic acids from alcohols. The starting carboxylic acid was soluble in dichloromethane, but insoluble in water. And we extracted that carboxylic acid into the aqueous layer. It was no problem. Well, here we can do something similar. We've got both cyclohexanamine and cyclohexanol. They're both soluble in dichloromethane. When we treat that with hydrochloric acid, we use 10% hydrochloric acid, that's going to protonate the cyclohexanamine to form the cyclohexanammonium chloride. So we'll get that ionic compound, which is now going to be water soluble. The cyclohexanol will remain unprotonated, so it'll still be cyclohexanol. And so when we shake this up, this will all dissolve in the organic or in the aqueous layer up here, and the alcohol will remain in the dichloromethane layer. We can separate those out, evaporate the solvents. So if we evaporate the dichloromethane, we can get our cyclohexanol back. And if we evaporate the ammonium or the water, we can get the cyclohexammonium ion. Hexanammonium. I'm having trouble saying that now, but we can isolate this in the water, and we can evaporate the water off and get this. We can also treat this with a base to remove the HCl and make it soluble in an organic solvent again. If we choose to do that, so that we don't have to remove water from it, we could potentially just remove another organic solvent from it. The point is, we have a way to separate this out, a useful method. All right, now we're going to talk about drugs again. There's so many different drugs that have nitrogen in them, so many different alkaloids and natural products, but also synthetic drugs that have these nitrogens in them. So this becomes a relevant topic. I'm not fixated on the drugs. I just want you guys to know that there's a lot of drugs that are like this. So let's go with something that's a pretty benign drug. This one is Benadryl. Benadryl, the base amine for this is diphenhydramine. So the diphenhydramine, here's our two phenyl groups, and then hydramine is this component. So that's the diphenhydramine. Well, diphenhydramine is not very water soluble. If you were to take this as a pill, it wouldn't do very much. This wouldn't give you much benefit because this is not going to be soluble in water, and so it's going to have trouble getting into like your bloodstream. So if you protonate it by adding HCl, you will create an ionic compound, which is the diphenhydramine hydrochloride, and that hydrochloride is water soluble, and it can dissolve in water, which means that it's possible for it to get into the blood and do its thing. So Benadryl is used as a treatment for certain types of allergies. I don't really like taking Benadryl because it makes me groggy, but for some people it works great. All right, so now we're going for the illicit drugs. Again, I am not encouraging you to do this. I am telling you some information so that when you hear about this, you say, oh, that's what they mean. So when people talk about free base, the free base of cocaine is this. So most medicinal cocaine, and I say this because there is medicinal cocaine. It does exist. It is a medicine. It is highly regulated, but it is available for doctors to use in certain applications. It is sold as the hydrochloride salt. So this is the cocaine, but when they protonate this amine, you'll get the hydrochloride salt. The hydrochloride salt is water soluble. This is definitely not water soluble. So if you treat that hydrochloride salt with a base, I'm not going to mention what base it is, but if you treat it with a base, you can deprotonate it and you can produce the free base of this cocaine. And that makes this, it makes it have a lower melting point because it's no longer an ionic compound, and it's also going to become more volatile, so it'll have a lower boiling point. And so some people will take this and they will smoke it. And when they smoke it, it can vaporize this cocaine into the vapor phase. It'll be the free base of that cocaine. And this is kind of what it looks like. Sometimes people will refer to this as crack cocaine. But that free base, when you vaporize it, it is now it will now absorb into the tissues in your lungs and go very quickly into your bloodstream. So it is absorbed much more quickly into your bloodstream. The downside of it is that it's absorbed much more quickly into your bloodstream. If you're a drug addict, that sounds great. But if you're a doctor and you're worried about that person who has taken this drug, it greatly increases their chance of having a heart attack, stroke, any number of things that will lead to death. It's very, very dangerous. So I wanted you to know what they mean when they say, oh, he was freebasing. Yeah, this is what they mean. If you see somebody doing this, get the heck away from them. All right, so now let's talk about the relative basicity of amines. So to understand the relative basicity of amines, we need to look at the pKa of the conjugate acid of that amine. So here is an amine. We don't know what the amine is, but here is an amine. And when we protonate that with an acid, a strong acid like HCl, we will form the conjugate acid of that base. We can tell by what the pKa of that conjugate acid is. The higher the pKa, the weaker the acid. The weaker the acid, the stronger this base is. So again, the higher the pKa, the weaker the acid, and the weaker the acid, the stronger this base is. Conversely, if we have a low pKa with this, that means that that's a stronger acid and that this base must be a weaker base. So there you go. That's one way we can compare how basic these bases are. So, factors that will affect the basicity. One, there's inductive effects. If we look at the electron density on the nitrogen atom, the greater that electron density is, the more basic that nitrogen is going to be. So anything that decreases the electron density on the nitrogen will decrease its basicity. Anything that increases the electron density will increase the basicity. So let's look at sort of a standard. So this is sort of our control trial here, which is ammonia. Ammonia, its conjugate acid is the ammonium ion. It has a pKa of 9.3. If we put an alkyl group onto ammonia, and instead we have, in this case, ethylamine, its conjugate acid is ethylammonium. It has a pKa of 10.8, which means that this is a weaker acid than the ammonium ion. But that means since this is a weaker acid, ethylamine is a stronger base. So by putting an alkyl group on ammonia, we turn it into a stronger base. That's because alkyl groups are electron donating. So alkyl groups donate electron density to whatever they're attached to. Now, there's some limitations on this. If you add another alkyl group, it doesn't do much to increase the basicity of this. There's reasons for that, but it doesn't do a whole lot. Once you've put one alkyl group on there, 2, 3 alkyl groups are typically going to keep it in the 10.8 to about 11.2 range. So there's not a whole lot we can do to increase that basicity with alkyl groups. If we compare an alkyl amine to an aryl amine, let's look at an alkyl amine like ethylamine and then compare that to aniline. So here is aniline. So what we want to do is we want to look at the availability of the non-bonded electron pair on the nitrogen. So how available is this to act as a base? Well, in ethylamine, that lone pair of electrons is localized on the nitrogen. It's not delocalized to any of the other atoms in that molecule. And because it's not delocalized, that's a pretty decent strong base. Again, pKa of about 11 for its conjugate acid. If we take an arylamine like aniline, and we look at its pair of electrons that's on the nitrogen, well, that pair of electrons can be donated to the ring, and we could increase the electron density in the ring. That's why ammonia is such a strong activating agent. But what that does is it decreases the electron density on the nitrogen. So it delocalizes it, making it a weaker base. All right. So by having that benzene ring, it makes this a weaker base. pKa for that is somewhere about 4. It's like 4 point something. I don't remember the exact number, but it's about 4 point something. So let's look at electron donating groups versus electron withdrawing groups on aniline. So if we have a substituted aniline that are either more or less basic than the aniline. So aniline, again, the pKa. All right, I just looked it up. The pKa of aniline is 4.6. So if we add an electron donating group to aniline, that's going to add more electron density to the benzene ring, which makes more electron density available for that nitrogen to act as a base. So by adding electron density, it will make the aniline more basic, which means the pKa of its conjugate acid is going to go up. So again, the higher the pKa of the conjugate acid, the weaker that acid and the stronger the base. So adding an electron donating group will make that pKa of the conjugate acid go up. So it'll make it a stronger base. If we add electron withdrawing groups to the aniline, the electron withdrawing groups are going to pull electron density away from the benzene ring, which is going to make, it's going to pull electron density away from the nitrogen and make those nitrogen lone pair electrons less available to act as a base. And in doing so, it will make it a weaker base. In other words, it'll cause the pKa of the conjugate acid to go down. We'll look at some of those numbers here in just a bit. So let's look at an electron density map that shows a picture of what I just said. So here we've got aniline as our control group. Aniline has a significant amount of electron density on the ring, but there's also some electron density on the nitrogen. That electron density on the nitrogen makes it available to act as a base. If we look at an electron withdrawing group like nitro group, and in fact we're putting this in the para position. So if you do para-nitroaniline, that nitro group is going to withdraw a significant amount of electron density away from the ring, making it much lower electron density on the ring, which is going to pull electron density away from the nitrogen. And in fact, if you draw the resonance structures, I encourage you to do this, draw the resonance structures for this, and you will see there's a resonance structure which donates a lot of electron density towards the nitrogen, puts a positive charge on this nitrogen here, on the amine nitrogen. By putting that electron density, pulling electron density, it makes this less basic. In other words, the pKa of the conjugate acid of this is going to go down. It's going to go way down. All right. Over here, we have an electron donating group with this methyl group. So that methyl group will add electron density to the ring, so make more electron density there, which makes more electron density available to the nitrogen, which means it's a stronger base. So we increase the basicity by adding electron donating groups, and we can decrease the basicity by adding electron withdrawing groups. What about if we compare an alkyl amine with an amide? Well, amines are much, much more basic than amides. So again, here we have ethylamine as sort of our comparison group. So ethylamine, that lone pair of electrons on the nitrogen, is localized on the nitrogen. There's no delocalization. It's a pretty strong base. pKa of the conjugate acid comes out to about 11. We talked about that one before. If we look at the amide, we can draw another resonance structure. We can delocalize the lone pair of electrons that's on the nitrogen. And when we delocalize that lone pair of electrons onto the nitrogen, we get a very significant resonance structure here that puts a negative charge on the oxygen. It does put a positive charge on the nitrogen, but that negative charge on the oxygen is quite favorable. And so that means we have a lot less electron density on nitrogen in an amide than we do in an amine. That means amides are just not very basic. So amides are not very basic. We're going to find that amides really aren't any more basic than other carbonyl compounds, or at least not much more basic. And so if we protonate an amide, it actually protonates on the oxygen, not on the nitrogen. The reason for this can be explained by looking at the possible resonance structures. If we protonate on the oxygen, we can do 3 total resonance structures for that conjugate acid of our amide. So when we do that, it will be there. If we protonate on the amine, we can't draw these additional 2 resonance structures, or we can draw 1 additional, but it's not going to be very favorable. So we can't draw both of these resonance structures. And so it turns out protonation happens on the oxygen, and there's been evidence to show that this is true. All right, so now we know that amides are not very basic at all. So amides are not very basic at all. So let's go to our in-class assignment. We're looking at number 20 here. This first one, this is a pretty easy one. So we want to compare, we'll start here. Actually, we'll start on these. I'm going to call this A, B. All right, hold on a second. A, B, and C. The least basic of these is going to be the amides. Amides are just not very basic, so C is going to be the least basic. Between these two, here we've got ethyl, cyclohexanamine, and here we have aniline. And as we saw, alkylamines are much more basic than arylamines, so B is going to be less basic than A. So again, this one will be the least basic, and the cyclohexanamine will be the most basic of those 3. All right, so now let's talk about heterocyclic aromatic amines. So heterocyclic aromatic amines. We've talked about this before, way back in our chapter on aromaticity. Go back and check out that chapter. If you go back and look at that chapter, there was a section where we talked about what happens when you have lone pair electrons on a nitrogen heterocyclic aromatic compound. And so here we're going to compare pyridine with pyrrole. Pyridine, if you look at the double bonds will account for 6 electrons. So those electrons that are in those p orbitals will account for all the aromatic hydrogens. As you recall from the chapter on aromaticity, we need the 4n plus 2 pi electrons, so either 2, 6, 10, so on and so forth. This one has 6 there. That means this lone pair is not needed for that aromatic ring, and in fact, that lone pair doesn't interact with the pi system at all. If you look at the symmetry, you'll find that lone pair is in an sp2 orbital, and it's perpendicular to the aromatic. It's perpendicular to the orbitals, the p orbitals in the aromatic ring, which means we don't really get any overlap of those. As a consequence, that pair of electrons is much more basic than it would be if it were in a p orbital. By contrast, pyrrole has a lone pair of electrons that is in a p orbital. As you can see, we've got 2 4 pi electrons that come from the double bonds. We need 2 more electrons to make this aromatic. Since we need 2 more electrons to make it aromatic, we're going to use those 2 electrons that are from this lone pair. And since if we do resonance structures with a lone pair of electrons, that means that lone pair of electrons is in a p orbital. That pair of electrons is not very available to act as a base. So pyrrole is much, much less basic than pyridine. And I'll show you how much less basic it is here in just a few minutes. All right, We also want to look at hybridization effects. What happens with hybridization effects? So let's compare the basicity of piperidine with pyridine. All right, piperidine with pyridine. Here, this lone pair of electrons is in an sp3 hybridized orbital. So that lone pair of electrons, sp3 hybridized orbital. In pyridine, as we discussed a few minutes ago, that lone pair of electrons is in an sp2 hybridized orbital. We're going to find that the more S character there is, the less basic that lone pair of electrons is going to be. So the higher the percent S character, the less basic it is. The more tightly held that pair of electrons is, and the less basic it is. So if we look at the conjugate acid of pyridine, it has a pKa of 5.3. The conjugate acid of piperidine is piperidinium, which has a pKa of 11.1. So about 11, about 5. That means that this piperidinium ion is a much weaker acid than the pyridinium ion. So this is a much weaker acid because it has a higher pKa. Well, if that's a weaker acid, that means its conjugate base is a stronger base. Remember, the weaker the acid, the stronger the conjugate base. The stronger the acid, the weaker the conjugate base. So stronger acid, weaker conjugate base. All right, so let's do a summary of all of these factors that affect basicity. We talked about inductive effects, resonance effects, aromatic effects, and hybridization effects. We're going to put those as examples over here so that we can compare them. So ammonia is kind of our baseline here, a pKa of 9.3. By having alkyl groups on there, it tends to push that pKa up, again, of the conjugate acid, pKa up to about 11, right? 10.8, 11, 11.1. Those are all close to 11, so we're just going to say they're all about 11. And it doesn't really matter whether we add one alkyl group or two alkyl groups or even three alkyl groups. It all comes out to about 11. So there's not a huge effect once you add more alkyl groups. But adding one alkyl group does add electron density and therefore makes that lone pair of electrons more basic, which means the conjugate acid would be less acidic. When we look at aryl amines, you'll see the pKa of the conjugate acids are much lower. And that's because the lone pair of electrons in aryl amines, here, the aryl amines, they're delocalized. And because they're delocalized, they're just not as available to act as a base. So their conjugate acids are much stronger. The stronger the acid, the weaker it is as a base. We do have resonance effects that come from these alkyl groups. So here, having electron donating groups makes it stronger than aniline. Aniline's at 4.6, and with these electron donating groups, they're somewhat higher than 4.6. By putting the electron withdrawing groups, for example, nitro here, look how low that pKa is, 1.0. So the conjugate acid of nitroaniline, paranitroaniline, is the paranitroanilinium ion, and it has a pKa of 1. That's pretty strong acid. That means this is a really weak base. If we compare pyridine with pyrrole, that's the one we were just talking about. So we compare the pyridine with the pyrrole. The pyridine, again, has a pKa of about, or conjugate acid, pyridinium, has a pKa of about 5.3, whereas the pyrrole, its conjugate acid is 0.4. That's a really strong acid, meaning this is a really lousy base. Amides, even lousier. So a typical amide has a pKa of about -1, and in fact, it's not even the nitrogen that gets protonated, it's the oxygen, as we saw a little earlier. Okay, let's look at number 21, and after that, we're going to stop this video, and we'll do the next section in the next video. So let's look at number 21. We want to rank the following ammonium ions in order of increasing pKa. So we want to start with the lowest pKa, in other words, the strongest acid, and we want to go up to the weakest acid. So our strongest acid here is going to be, we have three anilines. So we have an aniline here, here, and here. This one is going to be the weakest acid because it's not an aniline. We have this sp3, so this one's going to be the weakest acid. But these anilines, we need to look at the substituents. We have a methyl, a nitro, and a chloro. Well, the nitro is very strongly electron withdrawing, which is going to make this more acidic and have a lower pKa. So this has the lowest pKa. All right. In fact, we just saw on that on this thing here that the pKa of that nitro aniline is 1. So 1.0 for that one. So 1.0 for that one. All right. Then we've got chloro and methyl. Chloro is more electron withdrawing, and that chloro, it's going to be second lowest. So I'll put second lowest. All right. Oh, sorry about that. I just looked this one up. I don't have an exact value for it, but it's going to come somewhere at about 3.5. Again, I don't know the exact number for that. 3.98. I had it on another piece of paper. So 3.98 for the pKa of that one. For the methyl, this one is going to be it's going to be the third lowest or the second highest. I'll just put third lowest pKa. And the pKa for it, I looked it up, and it comes out to 5.1. Aniline itself is about 4.6, and when you put electron donating groups, it pushes it up a little bit, usually up over 5. So 5.1 for that one. And then this one, I don't know the exact pKa for it, but it's an alkyl ammonium. So this one's going to be the highest pKa, which means it's the weakest acid, and therefore the strongest, it has the strongest conjugate base. So this one is going to have a pKa close to 11. I don't know exactly where it is, but it's going to be close to 11. So so this is a pretty decently strong acid. This one's a little weaker, even weaker. And then this would be the weakest acid, which means it has the strongest conjugate base. All right. Well, that we're going to stop there. In the next section, we're going to be looking at using amines as nucleophiles. So we'll take advantage of the fact that amines can act as nucleophiles. So stay tuned for that next video.